Okay, so hello everybody. Welcome back for the Thursday conference of the Thursday of the conference. So it's a great pleasure to start this morning. In fact, so maybe I should mention that since Rita Pardini is not able to, for unfortunate reasons, not able to give her talk late in this, which is the second talk, Marco will also be giving her talk in her place in the second talk. But anyway, but this is Marco's talk now. Okay, so it's a great pleasure to have Marco Franciosi to speak on eye surfaces with one T-singularity.
Okay, thank you. First of all, I want to thank the organizer for inviting me to this wonderful conference workshop, and I hope we will be able to do it again in the next future, maybe physically. Okay. So I'm talking about the joint work with Rita Pardini, Rana, and Rollenske. The aim of the talk is to give a description, maybe partial, of the KSBA compactification of the moduli space M13. So now let me give the plan of the talk. I will give first introduction. Then I will speak about general arguments about existence and smoothability of surface or stable surface. Then I will treat the Gorenstein case. And the new part is the non-Gorenstein case. And I will end the talk speaking about further developments. So let me start. Maybe all of you know what we are talking about, but I can repeat it very quickly. We work over C, and we will talk about stable surface, which means an S2 surface, which possibly the following singularities in codimension 1 double crossing and codimension 2 SLC singularities, with the condition that the canonical shift is Q-Cartier and ample. Okay, so Zonke yesterday explained very well what does it mean, and we will talk about the Kollár-Shepard-Barron-Alexeyev compactification of MAB, which is the moduli space which parameterize stable surfaces with k square equal A and chi equal B. The case we are interested in, so our case, are eye surfaces. The name was coined by Phillips and is related to H surfaces, which means k square equal 2, and I surfaces, which are simpler than H square. We have k square equal 1, PG equal 2, and Q equal 0, which means that the Euler characteristic is 3. So the aim of the talk is to describe this picture, the compactification of M13, and this is work in progress. We have here a question mark since we are not sure that the picture is complete, and our description may be not exhaustive, but we want to show some evidence of what is happening. It is worth to mention the work of Green, Griffiths, Lazar, Robo, and their approach using Hodge theory. They showed a useful way to understand this picture globally. And our approach is different. As Zonke said yesterday, our approach is to study this moduli space pointwise. So we will treat each point of this picture. Okay, what does it mean, this picture? This picture means that we have a M13, which parameterize a smooth surface, and then it is included in the main component, which is called M13 bar smoothable. And we have some boundary divisor, just here, for instance, and some other strata of less dimension. But we have also here some new components which are not smoothable and which maybe are attached along a divisor. Okay, the red part is the M13 Gorenstein, which is an open subset. Okay, so this is the aim of the talk. Let's start with the analysis of M13. M13 is the Gieseker moduli space of canonical models of surface of general type with k square equal 1 and chi equal 3. The starting point is the work of Odekawa in 1976. He showed that M13 is unirational of dimension 28. Moreover, it showed that the bicanonical systems 2kx induces a covering of the quadric cone in P3, a 2-to-1 covering, branched over the vertex of the cone and a degree 5 upper surface section, which is degree 10 curves. So we have this map 2-to-1. We have delta, the branch divisor, and we have the vertex of the cone, and the fixed part of the canonical system maps to the vertex. And in this case, the canonical ring is easy to describe. The canonical ring of this surface may be described as follows. We consider x0, x1 of degree 1, y of degree 2, and z of degree 5. Then the canonical ring is isomorphic to the ring C x0, x1, yz modulo f, where f is a weighted degree 10 polynomial, which may be written in this way. What does it mean? Another way to see this description of the canonical ring is that we have injection of x in the weighted projective space P1125, and we have x is isomorphic to the variety defined by this equation f. It's important to see from our point of view that the bicanonical map, which is 2-to-1, induces an involution on x. And we will see it later again. So now I'm start talking about the second part. So I'm talking about general argument about existence and smoothability. Our approach is to study a normal stable surface using the minimal desingularization and then the morphism to a minimal model, which means contracting the -1 curve. And we want to understand the geometry of x via the geometry of y. So this is, as Julie explained yesterday, we have on one side a smooth surface, and on the other side, we have our stable surface. So for us, it's simple to study smooth surface. So we want to analyze the property of x via the properties of y. For instance, we can estimate the PG, the regularity Q and K square, looking at what is happening on y. If x is not normal, we may consider the normalization. We have here the D is the double locus, and D bar is the maps onto D. And so one way to study non-normal surface is to consider X bar and D bar. And this is well explained by Collar's papers. We have D bar can be seen algebraically via the conductor ideal of the home P lower star OX bar OX. And the philosophy is to consider X table not normal and as correspondence with X bar and D bar, which is a log canonical pair. But we will see it deeply in the next talk. So, in more general facts, how can we prove mutability? Our approach is to prove mutability studying the canonical ring RKX. And after that is to construct a family in such a way that we can deform the equation in a suitable weighted projective space. So without using deformation theory, just using algebra. But if you want to prove non-mutability, we can use geometry. So we have this proposition, which was suggested to us by Valery Alexeyev, which say the following. If we have a stable surface, and if we consider chi one parameter Q Gorenstein smoothing, we have X maps to 0 and chi maps to B. If we have a section of the automorphism of chi upper star over B upper star, B upper star, it means B minus 0. If we have a section, then what happens? Then up to best change, sigma, such section extends to a section sigma bar over chi over B, a global section. Here out chi over B means relative automorphism key. As a corollary, which is what we will use later, is the following. If we have a stable high surface, a necessary condition for being mutable is to admit an involution. So if X is mutable, then it admits an involution. And this is our general approach to study pointwise the moduli space. So let me now recall the Gorenstein case, which we studied a few years ago. So we consider the canonical ring RKX, which is the direct sum of the powers of the section of the power of the canonical divisor. And for Gorenstein I surface, it is easy to construct. Indeed, a canonical curve is irreducible of genus 2, and it is Gorenstein in this case. We have kx squared equal 1, so this means that we have irreducible curve and a section. So we take such a curve given by x0 equal 0, and we consider the restriction to C, which is half canonical. Then under our hypothesis Q equals 0 plus a Kodaira vanishing type results of U Rollenske, we have this surjection of the section of the multiple of the canonical divisor of X onto the multiple of L. And then studying here the ring RCL, of the half canonical ring on C via classical arguments of Castelnuovo, Mumford theory, and so on, exactly as in the smooth case. Here, the hypothesis Gorenstein and irreducible is fundamental. So we can recover the classical result. And we obtain that by the so-called hyperplane section principle, that RKX modulo X0 is isomorphic to RCL. That is, heading our section con 0, RKX is just isomorphic to CX0, X1, YZ modulo the ideal generated by F. And this is as in the smooth case. So it's really easy. As a corollary, we obtain that if X is a stable Gorenstein high surface, then X is mutable. Indeed, we have this injection into the weighted projective space, and X is obtained as the locus of vanishing of F, exactly as in the smooth case. In this case, F is a degeneration of the degree 10 equation of the smooth one. In particular, looking at this description, and we can consider the bicanonical map, and we have a 2-to-1 map onto the quadricone in P3. Okay, Ronke say, Kodarevan is not due to Wenfenmi. Okay, sorry. I learned it from them. So, looking at the bicanonical map, it's onto the quadricone. It is branched over the vertex and the quintic section, not containing 0. If you want Gorenstein, we need a section not passing through 0. We have this map, and we can obtain this map just looking at the canonical ring, since P112 is isomorphic to the quadricone. So we have P1125, and we map onto the first 3 components, and we obtain easily the bicanonical map. As a consequence of our description is that we can have a stratification of the moduli space of Gorenstein high surface, looking at the singularities of delta. So this is what we did with Zunke and Rita. We have a stratification depending on the singularities that delta may have. And we have this picture. Here is a stratification. I don't want to enter into the details of our stratification because it's an old story, but just I want to show the picture. And this one was described on Monday by Radu. So it's worth to mention the work of Greenleaf, Fitzler, Robles. They studied this. For the examples given by Rado was this one type of degeneration, which is an elliptic singularity. So we have this stratification with those are the number of singularities which came up in the normal case. So for instance, this is the smooth one, and we end with this one. So okay, now we want to investigate more the moduli space of I-surfaces. So we decided to see what happens in the non-Gorenstein case. And with the help of Julie, we decided to consider the case of high surface with a unique T-singular point, which may be the most easier case for normal surface, for non-Gorenstein singularities.
You mean the least hard case?
What?
You mean the least hard case?
Yeah. So we have X, a normal I surface, and assume that X has a unique non-canonical T-singular point P. What does it mean? Yesterday, Julie explained to us, I quickly recall. So we have a singularity of type, of this type, 1 over dn square, 1 dn a minus 1, which means a cyclic quotient singularity, locally as C2 model this relation given by xy maps to mu x, mu to the qy, where mu is a primitive root of the unity and q is a multiple with this condition, okay, which is relative prime to n. So our main result is the following. We have, for I surfaces, only the following cases exist. So we have the Cartier index, which is 2, 3, or 5. And for Cartier index 2, we have singularities of this type, 1 over 4d, 1 to this minus 1, and d is bounded from above by 32. For Cartier index 3, we have 1 over 18, 1, 5, only this kind of singularities. And Cartier index 5, we have 1 over 25, 114. So only these 3 cases. Furthermore, we have these interesting aspects. For singularities of type 1 over 4, 1, 1, and 1 over 18, 1, 5, we obtain divisors in the main components of M13 bar. Whereas the singularities of type 1 over 25, 114, give an open subset of a new reducible component of dimension 28. So this is why I draw the picture in this way. Those kind of singularities give new stable surfaces which are not smoothable. So let me explain how we did our construction. So let us start with index 2. Index 2 means that we have to keep in mind the construction. We have X, we have a resolution, Y tilde, and we have a map to a minimal model Y, as was explained yesterday by Julie. And we reverse this construction. So we start with a Y tilde, a surface Y tilde, and then we contract some string of rational curves. So in this case, we have in mind the bicanonical map, which maps onto the quadratic cone. So we consider F2, which can be seen as the resolution of the quadratic cone. We have sigma 0, 0 section, and sigma infinity, the infinity section with self-intersection -2. And we consider a divisor D in this system, 4 sigma 0 plus 2 gamma. and we consider a double covering branch over D. Here we may have some sort of singularity. Then we have our y tilde, and we contract the pre-image of sigma infinity. This is what we do. The result is a stable surface with singularities of type 1 over 4D. So here we get 1 over 4D, 1 to this minus 1. By contracting this. Okay, so let us count the dimension just to see if such surfaces give a divisor inside the main component. So this is how we did. Our surface X is determined by the choice of the branch divisor D, up to a finite number of possibilities. So the dimension count is simple. We consider the dimension of our system, which is 34. And we have also to consider the possible automorphism of F2. And what does it mean? That if we take a general D inside this system, 4 sigma 0 plus 2 gamma, we get minus 4 curve. For general D, the intersection with sigma infinities is just 2 points, and this gives us a minus 2 curve. That is, this minus 4 curve C obtained by pulling back sigma infinity is a minus 4 curve, and we get a 1, 4, 1, 1 point. So the dimension is just 34 minus 7, and we obtain 27. Moreover, in this case, using our description of X as a double cover, the quadratic cone, we can see that is mutable. Okay, the index 3 case is in the same philosophy, but we start with different Y. So we consider Y an elliptic surface with PG equal 2, Q equals 0, such that there exists a minus 3 section peak 0, and exists a unique I2 fiber C0 union C0 prime. We take A0, a singular fiber of type I1, and we let Y tilde over Y the blow up of Y at Q, which is the singular point of A0. So the picture is the following. Okay, so we start with Y, an elliptic surface. We have an A1 fiber, which we call A0, with a singular point Q. Here we have our singularities of type I2, and we blow up Q. So in the blow up, we obtain A, this curve. We have E is the exceptional divisor, and we consider the strict transform of B0 and C0. Okay, we have A, the strict transform of A0, B, the strict transform of B0, and C, the strict transform of C0. Then we have A square is equal to minus 4, B is equal to minus 3, and C0 is equal to minus 2. That is, we have a string of type 4, 3, 2. And we can contract it to obtain our surface X. Furthermore, to study this construction, we can consider the realization of such a kind of elliptic surface as a branched double covering of the Hirzebruch surface F6. We have branched plus a resolution. We have a branched covering over this curve D in sigma infinitives plus 3 sigma 0 with a singular point here. This singular point here gives us these two copies of rational curves giving an I2 fiber. And so to study X and Y, it's useful to consider this map. So on Y tilde, the composition, we have this map theta. So we have Y is the minimal resolution of theta bar, which maps to, which is simply the double cover of 6 branched of this curve, D in sigma infinity plus 3 sigma 0 with an ordinary double point. And we consider B0 the pullback of sigma infinity and C0 plus C0 prime the pullback of this fiber gamma 2 passing through P2. This description helps us to get information about the pluricanonical system. So we have this map, theta, which is the composition from Y tilde to Y bar to F6. And we have this map onto X. So if you want to consider the canonical ring, we may use this description to keep track of all the system. So the proposition is the following. The canonical ring of such surface is the following. We have C x0, x1, y, u, z, modulo 2 equation, the ideal given by 2 equations. One equation, this one is almost the same as the equation we see for smooth surface. And this is, the left one is a new equation. We have degree of x0, x1 equal 1, degree of y equal 2, degree of u equal 3, and degree of z equal 5. What does it mean, this description? That we have an embedding of X into the weighted projective space P11, 2, 3, 5 as a complete intersection of degree 3, 10. And this is helpful. So let me give you an idea of the proof. The idea of the proof is the following. We have the pullback of Kx onto Ky tilde. And this is the following. Ky tilde plus 2 over 3a plus 2 over 3b plus 1 over 3c. And luckily, we have that h0 of mkx is exactly as in the smooth case. This is 3 plus m minus 1 over 3. And we have no correction terms. There is this paper by Blach who show a way to consider the space of section of the pluricanonical system. And in general, we have correction terms, but in this case, all the correction terms vanishes. So what does it mean that H0 MKX is exactly the same as in the smooth case? This is helpful since it shows that the Hilbert function is the same as in the smooth case. So we have an idea that it may be smoothable. Moreover, one way to consider each space of section of the multiple of the canonical system is to consider the round down of the pullback of this is F, of the pullback of the multiple of the canonical sheaf on X. And we see it on Y tilde. And we use this description. So we have a computation of section and multiplication maps we using our geometric construction. So this is the next step. In order to study the canonical ring, we need to study the map of the multiplication of section. And so we use our geometric construction. For instance, we have H0 KX can be seen as H0 Y tilde of the pullback of gamma, a fiber, plus E, plus the exceptional divisor. And if you want to consider the pullback of 3 times KX on Y tilde, we have this one. It is theta per star of sigma 0 minus E minus C prime. So we have this very nice geometric description. And this is helpful for us to study the ring for multiple of 3kx. And finally, in order to consider the multiplication of section, if we consider the round down of f apostrophe kx and the round down of 2f apostrophe kx, we consider multiplication of section on y, which maps onto the sum of these two. And here we have a correction term, since indeed the map maps onto 3kx. So we need to add these correction terms. So this is why we did the construction of the multiplication map of the canonical ring. Finally, we use the involution used by y bar onto F6 to analyze the multiplication maps and find new generator. In particular, in this way, we find a good generator in degree 5. Multiplication map and counting dimension shows that we have a dimension 1 left. So we have to choose a new generator in degree 5. And using the involution, we found a good generator, which is stable under the involution. This is our geometric approach to study the algebraic part of the canonical ring. As a corollary, we obtain that a nice surface with a T-singularity point of index 3 is movable. And the idea of the proof is quite simple. Indeed, we consider a family in P11235 cross A1 over A1 with coordinate T, given by this couple of equations. And in this way, we have that for T different from 0, we get chi T general hypersurface in P1125. We can eliminate U. Sorry. if t different from 0, we can eliminate u, so we can eliminate the first equation. If t is equal to 0, we get our original x. So this is why we got this smoothing. And let us see that such surfaces give a divisor. So simply as in the above case, we count moduli. We count the number of parameters needed to be there. So such a surface X is given by the choice of Y and A0 and B0, which depends essentially on the branch locus D. We have the dimension of our locus of the systems of divisor linearly equivalent to D is 31. We have one condition for the double point, and we have the dimension of the automorphism of F6, which is 11. So counting parameters, we obtain 27, which means exactly that we have a divisor. We have no idea of what such divisor looks like. We simply counted dimension. So maybe people who is experts in knowledge theory may have a look and see what happens in deeper details. Okay, in the same fashion, we consider the index 5 case. So this is the so-called Rana-Urzua surface. We call it in this way, because in the paper by Rana and Urzua, they show the existence of such surface. So the construction is almost the same of the index 5. So we start with an elliptic surface with PG equal 2, Q equals 0 with a -3 section. And in this case, we assume that all the fibers are irreducible. We consider a singular fiber and we blow up the singular point Q, and we blow up a second infinitely near point to Q, lying on the strict transform of B0. So the picture is the following. So it's almost the same as in the previous case, but in some sense it's simpler. So now change the name a little bit. Now B0 is the fiber that we blow up twice. And we have this -1 curve, which appear on white tilde. And X is given by the contraction of this string ABC, where ABC are the strict transform of A0, B0, and C is the -2 curves obtained by the two sequence, the sequence of the two blow-ups. So that ABC is a string of type 3, 5, 2. And as above, we have this description. Now D is simpler than before. So now I'm going quickly. So the only things to remark is the following. In this case, the singular elliptic fiber a priori may be nodal or cuspidal. And we have different situations. So the proposition is the following. If we build X as above with B0 and a reducible fiber of type I1, which means nodal, then X is not smoothable. Moreover, such surfaces give a dense open set of M13 bar of dimension 28. So we have this new component of the same dimension of the main component of M13 bar. So the idea of the proof is to use the involution and to see that.
Franco,
See,
you mean you don't mean dense, you mean irreducible.
yeah, it is a dense inside an irreducible. Okay. Okay, if I say open, you're right. So, what is the idea of the proof? The idea of the proof is to use the involution. So, if x was mutable, then there should be an involution on x. So we lift such involution tau to tau tilde on y tilde. Such tau tilde preserves the exceptional locus and also the exceptional curve E with self-intersection -1. So preserving this configuration and the exceptional divisor E means that tau tilde of B is equal to B. Moreover, tau tilde fixes the intersection points with E, A, and C. But the genus is 0, and we have an involution which fixes 3 points, then it is the identity. Therefore, tau tilde induces an involution tau tilde 0 on Y, which fixes the image of B, which is B0, which is an A1 fiber. This is not smooth, and this is absurd since the fixed locus of an involution on an elliptic surface must be a smooth divisor. For the second part, from a result of Hacking Prokhorov, we have that every small deformation is equisingular, since otherwise we would have canonical singularities. So in this case, counting parameters as above, we obtain 28 moduli, exactly in the same way we did above. So we have a new component of dimension 28. Okay. So now let me show you an idea for the proof of theorem 1. So we start with X, an I-surface with only one T-singular point P, and we consider the resolution Y tilde onto X and the contraction to a minimum model. Since P is a rational singularities, we have PG of X equal to PG equal of PG of Y equal to, and Q of Y is equal to Q of X. And the results of Rana and Urzua give us that Ky squared is equal to 0. So putting all these things together, we see that Y must be a properly elliptic surface with PG equal 2 and Q equal 0. Moreover, setting R the length of a T-string, then using the result of Rana-Urzua, we have that only the following case occur. We have a bound for R minus D, and if it is 0, then the index must be 2. Therefore, we must have this kind of strings, of T strings. If R minus D is 1, the index is 3, and we obtain 4, 3, 2. And if R minus D is 2, then the index is 5, and we obtain. That is, we obtain the above construction. Okay, in the last minutes, I will quickly talk about further developments. So for the index 5 case, we are left with the possibility of B0 to being a cuspidal singular fiber. In this case, we have no contradiction on the existence of an involution. And the conjecture is that such surfaces are smoothable. We have evidence for this, and during Christmas holiday, Zonke talked with Stephen Kaplan, and maybe we have some smoothability criterion using some weighted projective space. But we haven't written yet the complete proof. So, and to conclude, just to give a picture of such eye surfaces, I want to give you some example, very simple example of non-reduced two Gorenstein eye surfaces. The first one is given by taking two quadric cones glued along D. And we map 2 to 1 onto our quadric cone. And this gives us an example. The second, maybe more interesting example, is given by two singular K3 surfaces glued along a rational curve C. And we have a map 2 to 1 onto two planes, which may be seen as a degeneration of the quadric cone. And this map 2 to 1 is branched over D, which is a quintic section. We have these 5 points on the line. And such points here give us 5 singular points. So we have two different K3 surfaces with 5 singular points. And in this case, it's nice to see that the canonical curve is given by a double structure on the intersection curve given by the two K3 surfaces. We have the difference in the sense of color is equal to 1 over 2 over C over the C reduced, sorry. And C is a genus 2 curve, a Gorenstein genus 2 curve, which is a double structure over a rational curve. And the third example is given by X1, a K3 surface singular, glued to an request surface along an elliptic curve with 3 singular points. And here this situation is quite subtle. We have a double structure over the elliptic curve. And in this case, the bicanonical maps contract the request surface to a line and maps the K3 surface to a plane. So the bicanonical map is not helpful to study. And Zonke found a proof showing that also this case is smoothable. But we have to consider the fourth canonical map. Okay, so I think I may stop here, and if you have questions.
Okay, so thank you very much for the talk.
Do I have a question?
Yes, please.
So a cheap way to get smoothings on these surfaces, the non-Gorenstein ones, is by computing the second cohomology class of the tangent sheaf. So I was wondering if you guys did the computation and what is the dimension for this second cohomology?
We Julie did it, but we found that, for instance, in the example where we have the difference of cuspidal and nodal, we have obstruction. So it's not so easy. We have an obstruction space. So in one direction, we can't deform. In the other direction, we can.
I cannot hear.
Sorry? So we did some computation, but it was not exhaustive from our point of view.
That was the case of 253?
It was,
you were talking about which example?
This example.
The 253?
Yes, your surface. Your surface, we have obstruction to deform it. Can you hear me?
And there you get homology ET?
No, we did not. We stopped computing cohomology because we didn't find the right way to keep track of the difference of the.
Because I was wondering what is the difference between the nodal case and the cuspidal case, and where maybe if if you have a divisor that's smoothable, I was thinking that maybe this H2 is 0.
And one direction, yes. Zonke, in this way, found a question which is stable under the involution in the cuspidal case.
So
Zonke, maybe you can answer.
Yeah. So also in the cuspidal case, you will have obstructed deformations because you have, I mean, it sits. It's not, everything is not written, but it should sit in the intersection of the two components. So the deformations will be obstructed in some way because the deformation space is singular. But the difference is basically, and you can see this also inside the canonical ring, that in the cuspidal case, the surface supports an involution. So the nodal case will not support an involution, but the cuspidal case will. And this means that you have this extra symmetry there. And then you can, I mean, we have some computation. They're not very well written, and I hope Stephen can make them work in a nice algebraic way. There you have the involution, so you have the quotient, which turns out to be a rather complicated rational surface, and then you can like deform the quotient to the quadric cone and thereby get your smoothing of the other surface. And in the nodal case, you don't have this. And for us, it was easier to actually compute the global geometry of the surface instead of computing the local, I mean, writing down the global family instead of working out the local deformation space, especially because there are obstructions.
So I don't know if there is a notch theoretical interpretation of the difference between cuspidal case of nodal case.
Hey, I had a comment, Marco, that maybe it's good to just consider the deformations of P112, or rather the generations of P112, because you mentioned my paper with Prokhorov, and there's a complete list of the
degeneration.
Yeah, and so I think they're relevant to your story. So for instance, there are surfaces, I was trying to write it down, but writing during the talk, but there's one that's a P129, and I think that's the one that explains the index 3 example, and then there's a P1950, which maybe explains the index 5. Have you looked into that at all? Or?
Not completely, but
Yeah.
it's a suggestion to.
I'm just saying it'd be an alternative approach, might be a bit easier to do than your calculations elliptic surfaces. And also, a really nice thing about that is that the deformation theory of the rational surfaces is unobstructed.
Yeah.
So, this delicate question about the cuspidal case having this other component, you won't see that if you think about it in terms of a double cover. You'll just see the, just see it on some unobstructed. I think you'll just see this main component that you're interested in.
Yeah.
And one other thing that just occurred to me, I'd never thought about this before, but if you, I have this paper where if you have a PG0 surface with a Wild degeneration, you get this distinguished exceptional vector bundle on the surface. Yeah, a holomorphic vector bundle on the nearby fiber that sort of tells you to look for that degeneration.
Yeah.
And now you have that situation where you have a PG0 surface, in fact, rational surface, you have a double cover, and sort of the deformation is coming from that. So you'll get some interesting holomorphic vector bundle on the double cover just by pullback from the base. Maybe it plays a role in the. There was this discussion yesterday. How do we see devices? In some other way. That might be a way to look at that in this case.
Yeah, thank you. It may be a nice way to see at it. Maybe later I will explain this, the way of considering obstruction deformation theory. So.
Could I kind of ask a global question, which is going back to your original picture with the M13 and then the other part? What's like the conclusion about what we know about that picture now, either proven or conjecturally? Yeah, that one.
Yeah. Well, what it seems to us is the following: we have no more components.
But so that's the first question. So you say you have a 28-dimensional additional component in the non-smoothable case.
This is one.
That's irreducible. I mean, for one thing, that's irreducible.
No, sorry, I haven't understood.
Your 28-dimensional new component, that's an irreducible component. There aren't several.
Yeah, this one.
And so do you know if that's the only one, or are you just conjecture?
It seems to us.
Yeah, okay, but that's a conjecture. I mean, that's not proven.
Yeah.
I would say it. I mean, I don't have any confidence about this. If it seems so to Marco, I'm fine with it. But I'm not underwriting this. And so
then when you're saying,
this is why I put a question mark, because we have different. I am confident.
And so then when you're saying you have these examples at the end, which are the smoothable ones with the double line stuff. Those are divisors in the middle that go on both sides, right? I mean, do you know that they have both a smoothable direction and a direction into the other component?
Yeah.
So what we actually know,
if the cuspidal one go to the nodal one, you got a non-smoothable.
What we actually know is, so what Stephen wrote down is a degeneration of the index 5 one, so in the green component, to a surface with, I forget the number. So we had this index 3 singularity, the ones which Marco showed, which form a divisor in the main component. And then Stephen wrote down a degeneration, a common degeneration of both, containing both singularities. So we don't exactly know that the cuspidal ones all are smoothable, but we know that the components are connected at least via a common degeneration of these two surface types of surfaces with one T-singularity to one with both T-singularities. So
yeah, but so I guess that, I mean, that part of my question is, because you give several different examples of smoothable things, do you expect those to be different irreducible components of that divisor where those two things meet? Right, the divisor between the green and the red sides, or whatever. Green and blue, that divisor could be irreducible, could have several components, right?
Right. I expect the intersection to be just the cuspidal ones, because that should be 27 dimensional.
I think the intersection is just a face of the cube, but we haven't.
So you guys think that that intersection divisor is just is irreducible also?
Yeah.
Okay. And then to get to the Hodge theory question,
it is not completely proved, so it is.
On the Hodge theory side, you'll have a variation of Hodge structure over the M13 thing.
Yeah.
And you should probably have like a variation of mixed Hodge structure or something like that over this other 28-dimensional thing.
I don't know.
Then I mean, I guess the question would be: is there some way of relating, the limiting mixed Hodge structure maybe of that variation of mixed Hodge structure and the limiting mixed Hodge structure of the smoothable one?
So I'm asking to the expert of theory.
Yeah, I don't know.
I suggest
that wouldn't be me, but maybe like Colleen or something like that.
Carlos, that's a very good question. We haven't thought about that.
I mean, a priori, there's not necessarily any reason why the limiting mixed Hodge structure from one, as we discussed yesterday, the Deline mixed Hodge structure is the same, but there's not necessarily any special reason why the two different limiting mixed Hodge structures would be related, but maybe they would be anyway.
No, nice question. Thank you.
Maybe this is the right point of view. Thank you.
Anyway, well, okay, so maybe I'll see if anybody else has other questions. Well, anyway, so thank you, Marco, for a nice talk.
Thank you.
Okay, so we'll reconvene at wait, I have to do the time change. We'll reconvene at 10:30 Miami time, right? And Marco will give Rita Pardini's talk at that.
Okay.